And if it's not squared, you can't use a Pythagorean identity. However, it would be nice if it was squared, right? So we're going to make a substitution, a basic use. What's that? I see what you're getting at, yes. I'm going to do it this way, though, which is the same thing as I think what you're saying. I'm going to replace x with u squared. If I replace x with u squared, then can't I use the formula you're talking about? Does everyone agree with that? If that x were u squared, then I could use 4 minus u squared under a root, and I could do trig sub. So let's replace everything. I replace x with u squared, and then I'm going to have to replace the dx, right? So this is a basic substitution I'm doing right now. I'm going to do dx is going to be replaced with what? So what's the derivative of this? 2u du. 2u du. 2u du. All right, now rewrite everything. Integral. So what's this top piece now become? Square root of 4 minus u squared, right? Over the square root of x, but that means the square root of u squared, which means it's just going to be u. And then what does dx become? 2u du. 2u du. You okay with where that came from? Take derivative of the right. 2u du. And these u's cancel. And so here's where we are. We are at 2 integral square root of 4 minus u squared du. And right here is your trig sub. You wanted it, right? You got it. Yes?
So I just get confused when you do the dx equals 2u du. It's like we've always taken it out, you know, it doesn't like the 1/2.
We've always taken out the 1/2.
We normally put the constant over on the left-hand side when you take it like that.
Yes, okay. That we've done when I've done a u substitution where I let like u be equal to, let's say, like x squared plus 1. Then the whole idea was to try and make, like, find something to match. Like we were trying to match this and solve for dx, weren't we?
And now we're like,
Well, now we already have it here. See, look, notice my substitution. My substitution is almost, yeah, it's not a true u substitution. I'm not replacing something complicated with u here. Like I'm not taking 4 minus x and saying, let's call that u. I'm actually taking something nice like x and replacing it with something complicated. So this is like a trig sub in the sense that I'm replacing x with something worse than x. But when I get to this point, I need to replace dx. There's nothing to solve for, right? Like here's what dx is.
How come you're allowed to just pull out a u squared? Like, is that something you just have to in the past we've used a substitution from something in the problem.
That's right.
So how come you can use u squared when it's not in the problem originally?
Well, that's your fault because you're the one who said to split it.
I mean, you said
And then you said it was that, right? You said it was that, and I said, wait, that's not squared. And then I helped convince you that if we were to replace x with u squared, then you could use the formula, and you seem to agree.
I mean, it looks fine.
Yeah.
I'm fine
So
with
your
x.
question is why? Well, I can take this x right now, and I could call it, a natural log of 4 plus b. I can call it whatever I want. Now, does that make anything better? I don't know. So you're always allowed to make a substitution of anything you want. I mean, there's certain parameters, like you wouldn't want to replace x with some imaginary something from...
Negative x minus.
Yeah, so there's certain things, but in general, you're totally allowed to replace anything you want with whatever you want as long as you're consistent with everything. Everything's got to be replaced. That's got to be replaced. That's got to be replaced. That's got to be replaced. Everything's got to switch. So, but we're here though. We're there, right? We're at a point where we can use trig sub now. So what would be the substitution I make? My trig substitution I'd make here. U is equal to a sine theta, which would be what? 2 sine theta. Okay, and now we've gotten kind of good at this. Sorry. And we're just replacing everything now. Right. Use 2 sine theta. The square root of all that crap's going to be 2 cosine theta, and the derivative of that, of course, is 2 cosine theta d theta. And we rewrite the integral. So now my integral becomes 2 integral, and the square root of all that's just 2 cosine theta, right? That's this piece. And then du, don't forget du, 2 cosine theta. Oh man, I'm going to have to power reduce, right? 2 factors of 2 come out, so I'm going to have an 8 outside. I have an 8 on the outside, yes?
Yes.
So it's really going to be a 4, isn't it? So, yeah. So what happened there? 2 came out, 2 came out. We have an 8 out here, but what was still here?
2 cosine squared.
Cosine squared, right? Cosine squared's here. And what am I going to do with cosine squared? 1/2, 1 plus cosine 2 theta. So the half came out, and now I have a 4. I'm not showing the steps. I mean, we've done this now, right? We've done this. All right. Oh, we haven't. Yeah, we've had that. Okay, so we have 4 theta plus 1/2 sine 2 theta. I feel like a scratch. No, scratch. I was going to say scratch record. What? No one listens to records, right?
Listen to dubstep. They have record players in dubstep.
I'm going to act like I know what you're talking about.
I don't actually listen to dubstep. I'm just making a joke.
I think I know what dubstep
It's
is.
techno.
It's like, yeah.
It's big bass beats.
Yeah. Okay.
I'll show you later.
Is this right? Is this right? Everything clear here? Yeah? Are you disagreeing? Okay. All right. Now, can we go the rest of the way? Could you take that the rest of the way? I think I'm done. Right. You got to go and make this right here 2 sine theta cosine theta. We've done that already, and then you got to go draw your triangle, and then we got to get everything back to from theta back to u, and then u back to x squared, right? Or was it? Wait, no. U would have been square root of x. Yeah. So, what's the questions? I see some.
We use different variables. So how would we?
If you what?
Are we solving for u then?
Yeah, you would have to get everything from theta back to u, which would require triangles. And then you have to go back to your substitution this, which means you would replace all your u, or all u's you see with square root of x. All right, I'm going to leave that as a ... You finish on your own. All right, let's take a little breath here. Yes. Are we gonna learn another technique before the next test? Next test is. Oh yeah, we got partial fraction decomposition. Yeah, and then after that we've got a couple of other things, but no more techniques. Yes.
Is the partial fraction decomposition that we're going to learn, is it in any way similar to like what we learned back in 1414?
Absolutely.
But just
So in 1414, you should have learned partial fraction decomposition. The reason you learned it is so that when we get to a problem here, that aspect of decomposing you should be comfortable with. Now I'm going to be honest, a lot of people have not done it in so long that we'll have to revisit it, but we'll be using it to tackle some integrals. All right, so we're still in the same section. I before we do the next problem, I just want to see how y'all feel about this. I'm just going to put something up here. And what I'm going to ask you to do here is to complete the square. All right, so this is going back to 1414 also. Complete the square. Now, I'm not asking you to like go do it, and I'm going to sit here and give you time to do it. I want us to talk through this. There's a way to do this, and there's a wrong way to do this, and I want to make sure everyone here is doing it the right way. So,
Isn't there like a formula
When-
a squared plus like AB minus B squared or something like that to solve these?
oh, a quadratic formula?
No.
No, oh.
It's like there's a formula for.
For completing the square is a formula?
I think so. No, that's something. Oh. Yeah, you were actually.
So what is the idea behind completing the square? What are you trying to do? Like you're trying to take that expression and do what with it? Turn it into what?
Something squared
You're trying to turn it into something squared plus, and it could be minus something squared. That's what you're trying to do. You're basically trying to turn it into like something squared plus or minus something squared. That's called completing the square. So let's see, anyone who wants to go out on a limb here and tell me how to proceed with this, I'll follow your path.
Add 8 to both sides.
Add 8 to both
Set it
sides?
to 0 and then add 8 to both sides. So that way you have 9x squared plus 6 squared plus 0. And then you just...
Well, hold on, back up. Add 8 to both sides. I don't have two sides.
Well, you can set the whole thing equal to 0.
Why?
That's how the positive completing square is.
Well, that's why we're talking about this. Your response is the best response I could have hoped for because it's the exact thing you can't do. Okay? And we're going to talk, I mean, obviously I'm bringing it up because too many people learn it that way. And the problem is with completing the square, most students learn it in the setting of an equation. And when you have it in an equation, of course you can do things to both sides. But when you don't have an equation, you can't. So when we do the problem we're about to do, this is actually going to be living underneath a root. So you definitely can't do anything with it, all right? It's trapped. Like there's no creating equations out of nothing. So how do you complete the square on a quadratic expression without having the ability to do anything to any other side because there is no other side? Anytime you add, you can subtract. So back in classes where you were taught, add something to both, add 8 to both sides, that thing, we can't add 8 to both sides. We can add it and subtract it on the same side. Okay? So let's do this. Anytime you complete the square, first of all, you have to be looking at a quadratic trinomial, which we have, right? Descending order, highest power of x down. First thing you need is that the coefficient on x squared must be a 1. So the first step is to factor out a 9. So I'm going to pull a 9 out. When I pull a 9, I have x squared plus, I pull a 9 from this, it's the same as that. Pull a 9 from that, it's the same as that. So now if I distribute that 9 back through, it's the same problem, right? Okay, so at this step right here, I'm saying that this line is equal to this line, right? Okay, now, once I have a coefficient of 1, the next step in the procedure is to look at the, well, I should probably reduce those fractions, yeah? At least that one. Let me reduce that one fraction. This is, no, 2/3. 2/3 x minus 8/9. Okay, just wanted to clean up that middle one. So now what we do is once we have a coefficient of 1 here, we look at the number, including the sign, the number in front of x. We're supposed to do something with that. Y'all remember? Divided by 2. Okay, so I take 2/3. I divide it by 2, which really turns it into what? 2/6, which is 1/3. So you're supposed to take that middle number divided by 2. What do you do with that answer? Square it. So you take that 1/3 and you square it, and that gives you 1/3 times 1/3 is 1/9. And this is our magic number right here, 1/9. This is the thing in completing the square back in college algebra that if you're taught with an equation, you're taught to add that number to both sides of the equation. Does that sound familiar to some of you? Is that me dialing? Did y'all hear that dialing? Is someone dialing? Someone? Okay. All right, so I'm supposed to take this 1/9, and since I cannot add it to both sides of an equation that doesn't exist, what I'm going to do is I'm going to insert it. Now watch where I put it. Plus 2/3 x, right here. Right here. You don't need to write this line. Let me write it first. Okay, do y'all agree that that's the exact same expression? If I add nothing right there after the 2/3 x, that's the same expression. So that nothing, though, is not going to be nothing. It's going to be that number 1/9. I'm going to add the 1/9, and then I'm going to immediately take it away. And then, so do we agree that that's still the same thing? Right? So if you do this, following this procedure, then your next line should be 9 out front. Okay, then here we should have these first 3 terms are guaranteed to be a perfect square trinomial. Guaranteed. So that should turn out to be x plus 1/3 squared. Always. This right here is this right here. If you don't believe me, take it and expand it out, and you should get this. Now, what's still there after that? Negative 1/9 minus negative 8/9, which is negative 9/9, which is minus 1. But that minus 1 is still in this parentheses, right? And there's still a 9 out in front of all that. Okay, that's it. All right, so the moral of the story here is if you've learned completing the square, working with equations, then you need to, especially as we move forward, you need to become comfortable completing the square where you have to take the number and add it and subtract it within the expression. Because you just, when an expression lives in an integral, you can't do anything with it. You can't work with two sides. All right, let's move on. There it is. Okay, so the problem we're going to do now is we are going to take the integral of 1 over the square root of 9x squared plus 6x minus 8. Yeah. Okay, so you look at that for a while, you're like, oh man, I really want to be an engineer. And then you say, yes, I do, because I'm persistent, I just keep going, I'm never going to quit, right? And then you decide, you know what, there's nothing I can do in terms of not trig sub, U sub or integration by parts or any of that. And then you have this little, like, whoa, wait a minute, I can complete that square, right? And when you complete the square of what's under the root, we just did that, right? So I'm not going to show that whole step. We know what's under that root turns out to be 9x plus 1/3 squared. Wait, hold on. I'll keep it pulled apart for now. Okay, dx. Do you all agree? Now, can that 9 come out of that root? Yes, 9 can come out as a 1/3. Okay, so by completing that square, I now have this 1/3 on the outside, integral 1 over square root of, in parentheses, x plus a third squared minus 1 dx. Yes? And man, if you just squint your eyes just enough, this looks like u squared, like the square root of like u squared minus 1, right? And that's kind of like a trig sub, isn't it? Like variable squared minus 1 underneath a root. So I'm going to make a real quick u sub, not trig sub. Just going to replace, everywhere I see x plus 1/3, I'm going to replace it with u. What's the derivative of that? What's du? dx. This is just a quick, all I'm doing right now is a quick substitution that's going to clean up that integral, make it look a little bit nicer. I'll still have 1/3, I'll still have integral, I'll still have 1 over, still have the square root. But instead of this thing squared, what is it? U squared minus 1. And then instead of dx, it's du. Okay, big deal. Nothing really changed too much with that basic u sub, just kind of cleaned it, right? And now that's your trig sub, right? Now, is this on your formula sheets? This one might be on the formula sheets. There are a few of these that are on your formula sheets, and this one is not. Oh, no, wait, hold on. No, it's not. Yeah, oops, okay, oh well. Well, we got to do trig sub then. Here?
I mean, in working with the formula, we just added a negative one.
Inside?
I don't know if that's
I'm glad you're bringing this up, because when I was I was trying to figure out if there's a way we could do that would make like this. Like, what's the big difference between these two? Like these two versions, because we do different trig subs on these, don't we? Why is it that we can't just take this and make it that one, or make that one by pulling a negative out? So let's say I pull a negative out of this, -1 right there. Then this becomes negative u, right? And then becomes +1. And then these two are the same, right? But now I have a -1 out there. The problem is you can't take the -1 out of the root, because that would be an imaginary number. And so because of that, you cannot just swap a negative, unfortunately.
But so we have a formula for that exact problem. It's
Which one?
The one you're pointing at, right?
Right here? Which formula are you looking at?
Like 27?
27. Yeah, there's no u out in front. 25.
Right?
Yeah, but it has a plus here.
All a -1.
No, because when you square it, it's still positive. Yeah. Yeah. Yeah, I mean, I wish there was a way around it. There's just not. Okay, so trig sub. Trig sub. Go, 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 go. Trig sub. So what's my trig sub going to be here? Secant theta. Okay, then what's the square root of all that stuff right here turn into? Tangent theta. Okay, and then what is the derivative of u going to be? Derivative of that. Secant theta, tangent theta. D theta. Right? And then finally, we rewrite it. 1/3 integral 1 over. 1 over what? Tangent theta. And then times du, which is secant theta, tangent theta, d theta. Are we happy about that? Oh yeah, we're happy about that, aren't we? Tangents cancel. What's the antiderivative of secant theta? Well, we did that last class, didn't we? Or maybe the one before that? Yeah, it was a natural log of some stuff. That was that one where I was like, no one would ever have come up with this. Someone suffered, but now we know it's on the formula sheet, right? So we know the antiderivative of that. So I think we're at a point where we could say we're there, because we have the antiderivative. We'd have to get everything from theta back to u back to x. But the critical parts of this are over. Questions? Okay, so let's do this. I'm going to give you an opportunity to redeem yourselves from the earlier quiz. If you're happy with what you turned in earlier, you're free to go. If you are unhappy with it and you want an opportunity, I'm going to give you one problem to do where you are going to work with just you, okay? And I'll let you use your notes, but you can't use each other. All right? And you only have 15 minutes. But you got to do this problem, you got to take it the whole way. All right? So, separate sheet of paper. Are you ready? Okay. You can use your notes. All right, here's what I want you to do. Take this all the way. There you go. And this concludes Trig Sub. It's you and your homework now, and we move to partial fractions next week.